Welcome back. To pick up our discussion where we left off previously, we were looking at limits graphically and numerically. We have yet to learn about any of the cool tips and tricks that you may know if you are a calculus veteran, or that you'll come to know if you're a calculus novice. But picking up, we're transitioning into one-sided limits, right? So we were looking at limits from both the left and the right side previously, and how that pertains to continuous functions specifically. So if you haven't watched that video, make sure you go back and watch it. But in some instances, f of x may approach the limit from one side of c without necessarily approaching it from the other side, and that's perfectly okay. That's information that we need to know that algebra was unable to provide us with. Or f of x may be defined only on one side of c. So if you think to yourself right now, well, what are situations or what are functions where that might be possible? Typically we see that in piecewise functions, okay? But we do need to establish a little bit of symbology here so we can all stay on the same page. So if you watched the previous video, okay, you would have noticed me put a little negative sign, but on the right side of our numerical value. That indicates that we are looking at the left-hand limit of whatever function. And yes, you guessed right. If we do a miniature plus sign, that would mean the right-hand limit. And then you think of the number line, right? Our positives here, our negatives there, right? So we're approaching a limit from the right. We're typically coming in from the positive aspect, and we're approaching a limit from the left. We're coming in from the negatives. Okay. So a little symbology. I will add. Drop the marker. That takeaway point. A limit can only exist, and I hate using those words, only and always. Ugh, the worst. Can only exist if both one-sided limits exist and they are equal. So we can say that yes, the limit exists from the right, and yes, the limit exists from the left. But if those two values, right, or the behavior of the function does not converge to the same precise value, we can't say that the limit actually exists at that value. Okay, let's see what this looks like in practice, away from the theory. Let's take a look at this function. The limit as x approaches 0 of x divided by the absolute value of x. And yeah, let's look at it graphically. So 1, -1, right? Because this is where we start to have the split, right? At 1 divided by 1, the output is 1. At 2 divided by 2, the output is still 1, so on and so forth, right? So we have this. Okay, at 0, the function is undefined. Go figure. And at -1, right? So anytime there's a negative value up here, it's going to yield a negative output. Right? So this is what our function will look like. And you might be sitting there wondering, like, oh, well, how do you know what these functions look like? Okay, just take some test points. Okay. Oftentimes in calculus, where you get a less rigorous, complex function the way you would in algebra 2 or pre-calculus. We're not really concerned with you being able to graph the function as much as you are able to elicit the information that we desire. But we clearly have to look at this from both the right and the left side. Graphically, we should already be able to intuitively tell what the limit is. Okay? But if you're not there yet, that's totally fine. This would be example 3 in my video series. So if we take a look at the limit as x approaches 0 from the left, okay, this part of the function does not change. This piece is going to change, right, because that's the absolute value. So when we are there, the function is behaving negatively. Okay, these would simplify and we're left with a -1, which is clearly the case, right? So from the left side, the function is tending towards that -1 value. However, if we flip the switch, no pun intended, to all my TikTokers, if you're watching this in like the year 2030, 2040, 2050 and TikTok is dead, Google it. From the right side, right, so the right side is all the positive values, so x remains positive, but once again these will simplify out and we're left now with a +1, which we can clearly see the case, okay, graphically, okay. As we become, you know, more advanced or more comfortable in computing limits, this will usually cease to exist unless we're strictly looking at it from a graphical perspective. Okay. If you're still a little lost on both of these parts, okay, we can see that all the values here are positive, hence from the right side, x retains a positive output, okay, but from the left side, x becomes, or yields a negative output, right, -1, -1, -1, -1, so we want to make sure that we accounted for that, okay. But that being said, we can clearly see that the limit as x approaches 0 from the left is -1, and the limit as x approaches 0 from the right is +1. Totally fine, totally okay. However, we say that the limit as x approaches 0 of the function does not exist because these pieces are not equal. So picking up where we left off, we've done graphical numerical investigations, and we dove into some one-sided limits. So to conclude, I guess, the different contexts that may arise, we have infinite limits. So some functions tend to positive or negative infinity as x approaches a value c. Since infinity is technically not a defined value, right? We can't really assign, or we haven't been able to assign a numerical value. It technically means that the limit does not exist. However, we do point out that the limit is infinite, right? We may say it's tending towards positive infinity, right? That the function is behaving where it's tending towards positive and or negative infinity. However, the reason why we need to do so is that when f of x approaches infinity or negative infinity, as x approaches c from either one or both sides of whatever c may be, that line, x equals c, right? Because we're going to have graphs, and I'll draw a graphical representation next to give you a little bit more clarity, is called a, algebra 2 word, vertical asymptote. Between me and you, I'll let you know a little secret as I erase this board. Calculus is nothing more than the young adult version of algebra 2. Algebra 2 is a teenager. Calculus is, I would say your age, 18, 19, 20, 21. The adult version of mathematics, I would say, is like Calc 4 and all your theory courses. But let's take a look at this function, since I love to digress. Right, so let's say we have the limit as x approaches 0 of 1 over x squared. Okay. Rational function. So we should anticipate an asymptote. Hint, hint. If we think about this, right, as these values, right, as we're going from the right and from the left towards 0, right, we're getting to decimal values, right? So let's start with a big number, 10. 1 over 10 squared, that's 1 over 100, so we're tiny, right? But if we get to 1/2, this becomes 1 divided by 1/2 squared, which is 1 divided by 1/4, which yields a 4. So graphically, right, at 10, we're down here at 1 over 100. At 1/2, we're up here at 4. And if we get closer and closer, right, so we can anticipate our graph. Oh wow, totally fudged that one. Our graph behaving like this. The reason why I know it's symmetrical is because of the even degree of the rational function. And let me get a different color. We know that we have, if you remember your algebra 2 rules, a vertical asymptote at x equals 0. So we can clearly see graphically from the right and from the left side, if we were Ant-Man or the Wasp walking along this function, we can clearly see that from the right and the left, it is tending towards positive or positive infinity. However, let's put out a warning. Do not treat infinite limits as true limits. And if you skipped the beginning of this video, I'll save those of you that didn't. Make sure you watch the beginning. Okay. The notation limit as x approaches c of f of x equals positive negative infinity is a shorthand way of saying that f of x increases without bound as x approaches c. So bottom line is to remember that infinity and negative infinity are concepts, not real numbers. And that'll do it for our introduction to limits.